And here's another famous example of beta decay. You take a radioactive isotope of carbon, which is carbon-14, not the carbon-12, the stable type. It can turn itself into nitrogen-14 with an extra proton balanced by the emission of a negatively charged electron plus an anti-electron neutrino. This is famous because we can utilize it to do what's called carbon dating or radiocarbon dating. The half-life of carbon-14 as a radioactive element through beta decay is over 5,000 years. That is a time scale which is just right for anthropology and archaeology. We're talking about thousands of years, not too long and not too short. Let's see how we can use that to our advantage. Okay, carbon dating. This is the reaction, beta decay associated with the physics behind carbon dating, and the dominant isotope of carbon found in nature on Earth, in the Earth's atmosphere, is carbon-12. Okay, the overwhelming majority of the carbon atoms in our body and in all living organisms is carbon-12 because it's a stable one. The unstable one will gradually decay and die away. But carbon-14 is also produced constantly in the upper atmosphere by reaction with cosmic rays, which high energy gamma rays. They come in and they can turn carbon-12 into carbon-14. So therefore, there is a balance between carbon-14 and carbon-12. There is a balance. Okay, I shouldn't say turn carbon-12 into carbon-14. I'm just saying that carbon-14 can be produced by means of cosmic ray bombardment from the outside in the upper atmosphere. So there is a dynamical balance in the Earth's atmosphere between carbon-14 and carbon-12. And this ratio in the Earth's atmosphere is about 1.3 parts per trillion. So for every trillion carbon-12 atoms, there are about 1.3 carbon-14. That's a very small fraction, but it's quite stable in the Earth's atmosphere. Okay, and the half-life of carbon-14 is 5,730 years. Now, how do we take advantage of that? All living things, such as a plant, such as humans and animals, whatever, when we are alive, we breathe in the air, right? And the air has this much ratio of carbon-14 and carbon-12. So in our body, there is also a dynamical balance between carbon-14 and carbon-12. And here is the same ratio, because we exchange particles, we exchange materials with the air, therefore it has the same ratio of R0. Okay, but when the organism dies, when the plant dies, when a person dies, there is no longer any air exchange between this organism and the atmosphere, and therefore whatever carbon-14 that's left in the body when it died will start to decrease, because you do not get any new carbon-14 by breathing in from fresh air, right? So the carbon-14 number will diminish over time. In fact, over 5,730 years, half of it will die, and therefore the activity will decrease by half. What's activity? R. R is given by dN dt, the rate at which reaction takes place, the absolute value, right? We saw that in the previous chapter. I mean, in a previous lecture. That's the definition called reaction. So how do we use this idea to do radiocarbon dating? That is, we found a piece of material, ancient material, several thousand years old. We want to determine exactly how old it is. So let's say we have a tree. Okay, we have remains from a tree. We want to know how many years since the tree died. Okay, so here's the thing. We can take a sample of mass m from that ancient object. Okay, we have to do only two measurements. One is the mass of the sample, m, which is easy to measure. Another thing is the radioactivity of carbon-14, that is R. You detect how many radiations per second you can get from this sample, R, which is easy to detect. Given m and r, I can find the approximate age of this sample. How do we do that? Here, this is how we do that. This much mass contains this many carbon-12 atoms, right? Okay, that's the mass, divided by the molar mass, which is 12 grams per mole, right? So suppose you have a 6-gram sample divided by 12 grams per mole, so that's a half a mole. Half a mole of carbon-12 multiplied by Avogadro's number, that gives you what? The actual number of carbon-12s in that sample mass N, right? But if you have this many carbon-12 atoms, how many carbon-14 atoms are you going to have? Just multiply this by R naught. If it's a fresh sample, right? If it's a fresh sample, that's the ratio. Okay, so the number of carbon-14 atoms when fresh is equal to just R naught times this. Okay, we call it N naught, R naught. That, again, is the number of carbon-14 radioactive atoms within a sample when it is fresh, when it just died. Okay, so this is the corresponding activity. Activity means, again, the number of decays per second from carbon-14. So you do that. We have this formula from the previous lecture, N naught e to the negative lambda t. You take a derivative, you get lambda times N naught. This ratio, this e to the power lambda t, I'm going to set it to 1 because that t equal to 0. Okay, you're just measuring it right now. You don't wait another 1,000 years. Just measure it when it's still fresh. You can get this lambda times N naught. That is the reaction activity that you're supposed to get, t equal to 0. Now, if you wait for 1,000 years or 2,000, whatever, a time t later, this activity will diminish because the number of carbon-14 radioactive elements has dwindled. The current value of R is lambda times N naught, lambda N naught. It is lambda N naught times e to the negative lambda t. So here is the difference. Here's the ratio of the reaction, and from that we can find t. Just take in a natural log of both sides, and there we go. So this formula tells you what is the time since the sample died. R is what we measure. Lambda is related to the half-life, which we know. Right? Lambda equals, there is a log 2 and there's T1 half. Remember that formula from the previous lecture? Okay, so you know what lambda is. Here's lambda. R naught is this. R naught is this. Mass of the sample, Avogadro's number, and the molar mass of carbon-12. All these things are known if you can measure R and measure the mass of the sample. So that is how you do carbon dating. It's very good for detecting the age of a living, one's live organism within the range of a few thousand years. If you want to measure the age of a rock, which can be a few billion years, you cannot do that, okay? Because that time is too short for geological time scale. Here's a famous example of carbon-14 dating, and that is the age of the Shroud of Turin. The Shroud of Turin is a linen cloth that is today housed in Turin, Italy, in their cathedral. On that shroud, there is an imprinted image of a bearded man, who supposedly was Jesus Christ. And the story behind the shroud supposedly was that this was the burial cloth of Jesus Christ. So when he died, they used that piece of cloth to wrap him, to wrap his body, and somehow the image of his face and the rest of the body got imprinted onto that piece of linen, and it's on display today in the cathedral in Turin, Italy. It is considered as a sacred object in the Catholic religion, but its authenticity has always been up to debate. In the late 1980s, 3 separate university labs each obtained a 50 milligram sample from the Shroud of Turin. These are University of Oxford, University of Arizona, and University of Zurich in Switzerland. And they each did a careful carbon-14 dating analysis. Okay, and what they found pretty consistent results among 3 different labs, and they found that the actual age of this piece of linen was about AD 1260 to AD 1390 with a 95% confidence. That is more than 1,000 years since Jesus Christ died. If you believe this, then it means the Shroud of Turin is a fake. It is not the real burial cloth of Jesus Christ. And the interesting thing is that this medieval time, about 1,000 years ago, that was also about the time the Shroud of Turin was first recorded to exist. So if you believe this, that these are not coincidences, believe the science behind it, then you would say that this Shroud of Turin really is just a fake. Somebody very cleverly made it up, and a lot of people still believe it. But this still is an open question. Even today, there is not a consensus despite this scientific measurement, it is still open to debate whether the Shroud of Turin is authentic or not. A lot of people still believe it's authentic despite this data. How do you dispute this data? Well, people found different ways to argue against it. For example, some argue that this piece of linen sample that was used in the labs were contaminated. How? Because on this very old piece of cloth, there could be layer of bacterial growth. These bacteria were once live organisms, and they could be much younger than the cloth itself. And these bacteria could then have its own carbon-14 reservoir, which is a lot more reactive than an old depleted sample. So this is an argument against that, but the labs supposedly did a careful measurement. So I don't know for sure who to believe in this case. You can do some more research if you're interested, and also a matter of how the image, which really looked like Jesus Christ, how this image got on this piece of cloth. And it's a fascinating story that's still ongoing. Okay, couple of things about beta decay. What is the so-called K capture? That's something we should know. In a beta decay, the nucleons would simply just emit an electron or particle, right? But in a related event, the nucleus can also capture an electron from its own atom. It eats its own one of the electrons from its own atom. That electron is usually from the K shell, which is the closest one. That's the shell that's closest to the nucleus. It got captured by this nucleus, which then changes from Z to Z minus 1, right? Because it absorbs an actual electron. Okay? And it produces an electron neutrino because you have to balance the, lepton numbers. Positive one here and positive one here. Okay, that's called K capture. That sometimes can happen. Another thing is I want to talk about how to calculate the Q value. That is how much energy is released in a beta decay. The idea of the Q value calculation is always the same. That is, you take the total rest mass before the reaction and a total before the decay, and a total rest mass of everything after the decay. Initial mass minus final mass. That is how much mass you have lost. The lost mass translates into the energy produced. That's the Q. That's always like M initial minus M final times C squared. Okay. Now M initial, that is the mass of this nucleus, right? I call it mx prime, prime indicating that we're talking about the nucleus only, not the atom, which included a Z number of electrons. It's just the nucleus. So you use a prime. And here, this is the Y nucleus, and then the electron. You just add those masses up. Okay, this guy has no rest mass, so that's part of the energy we don't count. Initial mass minus final mass, right? But the thing is, when we are given data about the masses, we usually given data only for the mass of the charged neutral atom, but not the nucleus alone. Okay, so we're given mx, which is different from mx prime. What's the difference? This is for the mass of the atom. This is for its nucleus only. Right? So how do we convert from mx prime to mx, my prime to my? Very simple. Mx, that's the atomic mass, minus the mass of the electrons outside. That is the mass of the nucleus, right? So it's mx minus z electrons. Z times mass of the electron, that's mx prime. My prime, same thing. My, it's got Z plus 1 electrons, so we have to take the atomic mass of element 1. Cancels out. Okay, all this ME just happen to cancel out. So it doesn't matter whether you use the mass of the electron, or whether you use the mass of the proton, or I mean the nucleons, or the mass of the charged neutral atoms. In fact, using the mass of the charged neutral atoms is actually easier this way. It's just mx minus my. These are atomic masses. Okay, not nuclear masses. Minus times c squared. That's it. That's for beta negative decay. But for beta positive decay, believe it or not, the answer is actually different. Here is the beta positive decay. So you start with this many protons. You end up with Z minus 1. One less proton plus a positron. And we can take a look at how this works. Okay, again, it's initial mass minus final mass. Initial mass is the nucleus of this guy. Final mass is the nucleus of that guy plus the mass of the electron, which is the same as mass of positron, which is the same mass of the electron. So that's that. I'm just trying again to indicate the mass of the nucleus, not the mass of the atom. Now, do the substitution as we did here. Mx prime is equal to mx minus zme, mass of the atom, mass of the nucleus. Here, same thing. Mass of the atom, mass of the nucleus. The difference is this many electrons. And don't forget there is also an additional mass of the positron here, which is the same as mass of the electron. But this time when you do the algebra, you find the mass of the electrons do not totally cancel out. There is an extra term, minus 2 mass of the electron. Okay, so this is, just pay attention to this. Right? It's a little different. It's because, again, we usually give you the mass of the whole atom. So you have to take that in consideration, even though the actual beta decay only involves the mass of the nucleus. So that's why you have this subtle difference. All right, the last one is the gamma decay. In the gamma decay, what's emitted is a high energy photon. In fact, it's got highest of all photon energies. It's called a gamma ray photon. There is no change in atomic number A, atomic number Z, and atomic mass number A. What you have here is the nucleus in its excited state. It's got more energy than usual. It's not in the ground state, so we use a star to denote it. And it goes down to the ground state and shedding its excessive energy in terms of beam of pure energy, which is a photon. And the gamma ray photons typically have energies of several MeV to several GeV. G is 10 to the 9. So we're talking about extremely energetic photons, each carrying between 1 million and 1 billion times the energy of a visible light photon. So they are very lethal. They're extremely energetic, very powerful. No change in A and Z. Here is an example from the textbook. Boron, in excited state. In fact, boron is not in excited state, but boron can just take a beta decay into an excited state of carbon-12. Okay, which then gamma decays to the ground state of the same nuclide, producing a gamma ray photon of 4.4 MeV. That's the energy difference between the excited state and the ground state of the carbon-12. So that's an example of gamma decay. And gamma decays can be used for many purposes. And sometimes it's something we need to avoid. Gamma decays, because the photons are extremely energetic. If you expose yourself to gamma decay, a large amount of radiation dosage, you're going to get very sick. In fact, you will get leukemia and so on. So you need to shield yourself away from large dose gamma decay. On the other hand, you can also use it for medical purposes if you control the dosage and the region of radiation very carefully. The so-called gamma knife is a prime example. Gamma knife is not a real knife. It is really it's a machine that produces multi-beam gamma rays, highly collimated with a certain amount of radius. And these gamma rays can be directed to focus on a certain region in your body or in a patient's body. It is particularly useful to treat brain cancer. If there's a small tumor in the brain, whose diameter can be as small as 0.2 millimeters. Then by focusing multiple beams of gamma rays, there will be a region of very strong radiation which happens to coincide with the location of the tumor. You can destroy the tumor that way without opening the skull. Think about that. So it's a painless procedure that is highly effective for treating early stage brain tumors. And the source of this gamma ray is cobalt-60. Okay, cobalt-60 star, which means it's an excited state. It de-excites into ground state, producing a gamma ray photon. The gamma knife device is very expensive because we have to use heavy lead shielding, so that this, well, because the cobalt-60 would radiate gamma ray in all directions randomly, but you have to produce highly collimated beams shielding everything away from every other direction. So you have to use very heavy lead shielding. Therefore, the device itself weighs about 20 tons with heavy lead shielding, 20 tons. And even the floor that houses this gamma knife device has to be strongly reinforced because it's very, very heavy, much heavier than usual. So that's an example of how we apply medical usage of gamma rays.